compute the double integral over the region R of the function 1 plus y squared over x squared, where R is the sector bounded by the lines y equals 0, that's the x-axis, y equals x, and the unit circle. So this is a sector of a circle, and we would like to use polar coordinates here due to the nature of the region, and also the integrand, as we shall soon see, is very nice in polar coordinates. Polar coordinates, x is r cosine theta, y is r sine theta. So the ratio y over x is sine theta over cosine theta, which is simply tangent theta. So if we use polar coordinates, this becomes the double integral of 1 plus tangent squared theta, and the differential dA becomes r dr d theta. And in this region, that's the unit circle, so r goes from 0 to 1, and the line y equals x gives us a 45-degree angle, so theta goes from 0 to pi over 4. Now this integrand, the 1 plus tangent squared theta is a constant as far as r is concerned, and so we can take it outside of the r integral, and this becomes the integral from 0 to pi over 4 of 1 plus tangent squared theta times the integral from 0 to 1 of r dr d theta. Now this integral is a constant and can come outside of that integral, and that gives us the integral from 0 to 1 of r dr d theta, of r dr, times the integral from 0 to pi over 4 of 1 plus tangent squared theta d theta. So this integrand, 1 plus tangent squared theta times r, it's what we would call a separable function of the variables r and theta, because it's a function a function of r times a function of theta. And when that happens, as you can see, we can just integrate the function of r and multiply by the integral of the function of theta. Okay, so the integral of r from 0 to 1, antiderivative is r squared over 2, plug in 1 and 0, and we get 1/2. And for the second integral, we have to use the identity. 1 plus tangent squared is secant squared, and then the antiderivative of secant squared is tangent. So we get tangent, and we have the 1/2 here as well, which I forgot to write, so I'll put it at the back. And the tangent of pi over 4 is 1, the tangent of 0 is 0, so this is just 1 times 1/2 is 1/2. So polar coordinates, y over x is tangent theta. So here we have 1 plus tangent squared, which becomes secant squared. Antiderivative of secant squared is tangent. And we had a separable integrand, and so we could integrate the theta function and the r functions separately. Okay, let's see what happens here. In the second one, compute the double integral of xy, where r is a portion of the closed unit disk, where x is positive, y is positive, and so we have just in the first quadrant this quarter of the unit disk. So this in polar coordinates, we're going to get double integral. X is r cosine theta, y is r sine theta, and dA is r dr d theta. And the bounds, r goes from 0 to 1, this is the unit disk, and theta in the first quadrant goes from 0 to pi over 2. So this is another separable function. So we could integrate the theta first, integral 0 to pi over 2, sine theta times cosine theta d theta, times the integral of the r function, 0 to 1, r, makes r cubed dr. The integral of r cubed from 0 to 1 is 1/4. And then to integrate sine theta times cosine theta, we can use the u substitution. U is equal to sine theta. Du is cosine theta d theta. So we get 1/4 integral of just u, not sine u. I was about to write sine u, but u is just sine theta. And then this is du. So this is just the integral of u. Now, what are the bounds? The bounds, when theta is 0, u is the sine of 0, which is 0. And when theta is pi over 2, u is the sine of pi over 2, which is 1. And the integral of u is du. And the integral of u du is u squared over 2. And when we plug in 0 and 1, we get 1/2. So we get 1/4 times 1/2, which is 1/8. So this is polar coordinate transformation with a very special ratio here. Y over x is tan theta. And in both examples, we had separable integrands. That means that we have a function of theta times a function of r, and when you're doing a double integral, then it just turns into the product of two integrals.